setup. This is Valentin Féray, and he will talk about Graphon limits and large independent sets in uniform random cographs.
Yeah, so co is very important.
Cographs is very important. So tell us all about it.
Yeah. So thank you very much. Thank you for the introduction and thank you for the organizer. I'm really happy to be here and I really enjoyed all the talks so far. I hope I'll enjoy the next one also. So this is a joint work with a series of authors, Frédéric Bassino, Mathilde Bouvel, Michael Drmota, Lucas Gerin, Maazoun and A, Pierrot. And yeah, we are studying this random cograph. So I don't know if you know what a cograph is. If you don't, you will in a minute, hopefully. It's just a name for graphs which avoid P4, so the path with 4 vertices, as an induced subgraph. Okay, so here you can check it maybe, but that's a cograph. But if I add an edge here at the bottom, that's a disconnected cograph. If I add an edge on the bottom, now I have an induced copy of P4, so I'm not a cograph anymore. Or if I remove that edge, I have my disjoint copy of my induced copy of P4, and I'm not a cograph. So this have been studied in a variety of domains. We'll see an equivalent definition a bit later on the talk. They are also called complement reducible graph. And the question I want to discuss in this talk is, if you take a uniform random cograph with n vertices, what can you say about it? And I will discuss 2 aspects of that question. The first is what is this Graphon limit? And the second one is, do we have large independent sets and cliques? And there are some motivation for that. It can be, look a bit arbitrary, say it like that. But in fact, this case where we avoid P4, if you compare to other family of H-free graphs, it's rather special. So I will explain why in the first part of my talk. And the limiting objects, the limiting Graphon object turn out to be rather different than what you can see in other cases. And I want also to convince you that it's an interesting, really non-trivial limit that we find here.
So one of the important points here is that you're dealing with induced subgraphs, right?
Yeah.
So there are not allowed to be any edges along the 3-edge path.
Exactly. So that's why here I have a 3-edge path. Here it's induced, so that's not a cograph. I had it here also, but here as an induced subgraph, you will find the 4 cycles. So it's here, this one is a cograph.
I see. Thank you.
So it's not a monotone class. Sometimes by adding edges, you violate the condition. Sometimes by deleting edges, you violate the condition. So it's really as induced subgraph. And yeah, and for this second question, the reason we look at, I will tell it in the middle of the talk on, so it's related to what is called what's famous conjecture in graph theory, which is Erdős-Hajnal conjecture. But okay, it's just related. It's not really giving any intuition on that, any really progress on that. Okay. So the first part, before going to this Graphon limit and independent sets, I want to discuss how asymptotic enumeration of H-free graph in general and on cograph in particular. There will be no new result here. It's more for me a way to show you a bit the structure of this H-free graphs and an introduction to the rest of the talk. Okay, so let me try to explain you, not to give you directly the result of what asymptotic result on enumeration of H-free graphs, but to tell you where it really comes from. So imagine, if you want, I will just explain lower bound because it's easier. You just construct some H-free graphs and count them. And if you want to say you're given an H and say it's chromatic number, so then chromatic number, I think it will be 5 in my example. So then there is an easy way to construct a lot of H-free graphs is to consider graphs of that kind. So what I mean by of that kind, you take a 4 colorable graph. So it means you take 4 independent sets and then you can put whatever you want in the middle. So of course, this will avoid H. in fact, not only as induced subgraph, but really a subgraph. And it's an easy counting exercise to see that there are roughly 2 to the 1 minus k, 1 over k minus 1 plus a small o of 1 times binomial n2 such graphs. So basically the proportion of edges which are inside, proportion of potential edges of the complete graph which will be inside one of this bubble, if you take this rather balance, will be 1 over k minus 1. So here k minus 1 is 4. And that's why you have to remove that here. Okay, so this gives you a first lower bound on the number of H3 graphs with n vertices. And this will work also if you look at things avoiding H as subgraph. But now we want induced subgraph. So you could also do the same with, say, taking H bar instead of H. Because of course, this notion of induced graph, you have the number of H3 graphs will be the same as the number of H bar 3 graphs. And which means in terms of my picture here is that H bar will be the complement of H. Sorry, so you just, so that's the complement of H. So in terms of my picture, it means here, if like my chromatic number of H bar is 5, then I will put cliques in all of this set, and I will construct a lot of H3 graphs. Okay, and in fact, I can also play and put sometimes independent set and sometimes cliques. And what you get at the end is that you will get this bound not only if the chromatic number of H is k, but more generally if you can partition your, or if you cannot partition your set in your vertex set of H in S cliques, so and T independent set for some S plus T is equal to k minus 1. So, and then you can really take the best k, which the best k which satisfies that. And in fact, what was proved is that this gives you the good asymptotic enumeration. I mean, the good exponential, the good order of magnitude in the exponential term when you try to enumerate H3 graph. So that's this theorem. So the definition of this R is a bit complicated. It's the maximal R such that you cannot partition things into S cliques are independent sets. It's something that R plus 1 is called the coloring number of H. So it's a variant of the chromatic number where you not only consider partition in independent sets, but mix partition in cliques and independent sets. And okay, the hard thing to prove is that this is indeed that you have a matching upper bound. I'll show you how to get the lower bound. That's easy, but the matching upper bound is a bit hard. So why now?
The cliques are the independent sets of the complement, right? That's how they enter?
Yeah, exactly. But then you can mix cliques and independent sets. So it's not only, this will be smaller than, no. This will be at least the maximum of the chromatic number of your graph and of the complement, but it can be bigger because you can mix cliques and independent sets.
I see.
And the thing is that it's hard to have such a number small. Okay, here you see that the case, if R is equal to 1, this is really particular because if R is bigger than 1, you really have something which is exponential of theta of n squared. But if R is equal to 1, you have something of smaller order of magnitude. So the case R equal 1 is interesting, but R equal 1 means that you need to be bipartite, your complement need to be bipartite. So you already see that there are not so many cases, and you need in fact a bit more. And basically P4 is one of the first few cases. So you have the edges, P3, you have very trivial case, but P4 will be one of the few cases where you have really here a subquadratic bound here. And that's why P4 is special. And in fact, these cographs are rather easy to enumerate by other methods because they have a very nice recursive structure. And so this is a result from the early 80s that in fact you have an equivalent definition of cograph as the set of graphs which can be obtained by iterating these two operations. So this is just taking disjoint union, and this is taking disjoint union with a complete Barthéad graph and adding all the edge between the two sides. Yes?
So can you go back to your previous slide?
Yeah.
So what if H is bipartite?
If H is bipartite,
Then R equals.
no, it's the coloring number. It's not the chromatic number. So
it's the
usually you
coloring
will
number.
have like the complement of H will not be bipartite, and you will have a bigger R in most cases. So that's, yeah. So you can obtain cographs by iterating this thing, and that's really an if and only if. If you avoid P4, you can be constructed like that, and if you can be constructed by iterating this operation, you avoid P4. And once you have the statement, that's not very difficult to prove. So that's why they are called complement reducible graph, because another way to say is that they are obtained by disjoint union and taking complement, because this is just the complement of the disjoint union of the complement. So, okay. And once you know that, you can really encode your cographs by a tree, which tells you which operation you've made to construct your cograph. Okay, so here, for example, this cograph that I had at the beginning, to construct it from vertices by using these two operations, what should I do? I should take, on that side, I should take 3 vertices and do joins between them. So here I'm already using that this join is in fact an associative operation. So I use it for more than 2 graphs. And for that side, it's a bit more complicated. I start with 2 vertices on one side, I do a disjoint union. I start with 3 vertices, I do a disjoint union, and then I do a join in between. And then I took my 2 pieces and I do a disjoint union. So I think you see how I go from at least more from the tree to the cograph. It's just by iterating things. And in fact, the tree representation will be unique if you impose that you have alternating decoration, this union and plus I will call that decoration. And once you know that, you can use techniques from analytic combinatorics and have some very precise enumeration results. And we see that indeed it's exponential of a small o of n square. In fact, you have the n factorial if you count in the label case, but then it will just grow exponentially, and you can say what is this constant. You could also say what is this constant c, and you have this n to the minus 3/2 term, which is really typical from when you enumerate tree structures. Sorry. Okay, so that's the enumerating part, and we see already some why cographs are a bit special in this story. So now I will come to the topic of the workshop, and we will discuss Graphon limit of this model. And I'm interested in really taking a uniform random graph, avoiding a given h as induced subgraph, and to say something about the Graphon limit, if it exists, of course. Yes.
Just going back to your previous k to kappa to the n, is there a representation of what you're constructing as some sort of multi-type branching process conditioned to be of size n or something?
So yeah, in fact, if you just want to count, you can even do it with just one type, because there is a symmetry between union and plus. Or another way to say it is that if I told you that this thing should alternate, so I only need to give you the decoration of the root and you can recover everything. So which means up to a factor 2, you can forget about this type. So it's really, if you want to count, it's really one type branching process. And you can, for example, a uniform random cograph will give you a tree, which is a condition, Galton-Watson tree condition to have a given number of leaves. I don't know if that answers the question. Yeah, exactly. And we'll use that. Okay, so that's.
Can you understand the kappa in terms of that branching process?
Probably, yeah. I will not say. Yeah. So kappa will come. You need if you want. So here you have the possible degree output. So I didn't say, but I don't have degree 1 vertices. So you have a list of possible degree output. You have to tilt that with some power of kappa to get a probability distribution and to get a with mean 1.
Yeah,
and that's exactly this kappa.
I see. Thank you.
A graph. Can you say this construction? They give you a graph. Can you say it came from a cograph?
Can I say if it's a cograph?
Yeah.
There are algorithms to do that, but I don't know exactly how they work. But yeah, I think you can do it in linear time. Yeah, you. Okay, so that's the question we're looking. So in the case where, I mean, this theorem is general. It works also for cographs. It gives some somehow partial answer that this Graphon limit of H3 graph, typical Graphon limits, they are rather special. So they look all a bit like that. So it might be just subsequential limit. I don't know if the limit really exists. In other terms, what I'm describing here are the Graphon which are H avoiding and have maximal entropy, if you prefer this language. And they are more or less stochastic block model, except that, okay, so I cut my thing into R blocks. So the R is exactly the same that we had before, that appeared in the asymptotic enumeration. And in the outer diagonal block, I just put 1/2. Why it's not really a stochastic block model? Because here I don't necessarily have a constant function, but what I know here is that it's 0, 1 value. So here I don't know if you can read it. What is important is that it's this curly bracket. So it means it can also take value 0 or 1, nothing in middle. Okay, so that's already gives some intuition. Somehow for me, it's not a proof. It's not even a complete sketch of proof, but it's a bit reminiscent of that picture. You know, when you have all these edges, this gives you 1/2 thing. And here you don't exactly know what you have. Yeah.
So in this construction, how many edges does this have? Is it close to the extremal number? So in this construction, how many edges does the Graphon have?
How many edges does the Graphon have? For this part, I don't really know. Then here you will have like a function close to 1/2 if when R is big.
Yeah, I'm sort of trying to understand how far is the number of edges from the extremal number.
It's far.
Yeah, because you
it's like replace for triangle.
For H3 graph, if you want, you can put you can just take the complete graph unless H is a clique. But then there is a notion, you have to twist a bit the notion of extremal graph if you want to give it a sense in this context.
I mean, if you really just care about number of edges, it's far. It's like complete bipartite would be extremal for triangle, but you would rather get a random bipartite. So that would be 50% of if you count the edges, but it's sort of a typical triangle-free graph.
I'll replace this 1/2 by 1, and it will still probably be H3, but then you will have a smaller entropy. So it's, yeah, we are not optimizing edges count in either direction. Okay, but okay, for P4, it just tells you basically that you have one block, which is 0, 1 value, and somehow we already know that any P4 avoiding Graphon is 0, 1 value. That's not too hard to see. So what is the limiting Graphon for P4? And so we have this result, and which was also independently obtained by Stufler, that if you take a uniform random cograph, so I said you have two ways to define that, labeled or unlabeled. I don't want to go into the details. The theorem works for both. And then you take the associated Graphon, it will converge to some random graphon. So it's a convergence in distribution in the space of graphon, and which is related to the Brownian motion. So we called it Brownian cographon. And here is the description of how you construct it. You start with a Brownian excursion, E, so I mean Brownian motion, which starts at 0, comes back at time 1 at 0, and is always positive. And you have to add some randomness. You have to take random sign to assign random sign to each of its minimum. And then what we will do is, if I take xy in 0, 1, so I can, I don't have put that on my picture, sorry, so I should have done that. So xy are in 0, 1, so that's my interval 0, 1, so I can imagine I have points in my excursion. Then I look at the minimum of the excursion between x and y, and I look what sign I see. If I see a minus, I just put 0 for my graphon, and if I see a plus, I put 1. So I will give an intuition of why this is a good definition in the next slide, but that's just the definition for the moment. Sorry? No, so you look at the minimum of the excursion on xy, it's almost surely unique. So you will see some minus and plus, but you really look at the minimum, which has a minimal value. Global minimal on the interval. And if you want, that's a simulation. So that's a uniform random cograph. And that's the adjacency matrix, with 1 being black and 0 being white. And we see that it has a rather rough structure, a bit with some self-similarity, which, okay, is related to the fact that we have this Brownian limit. I will try not to do a proof, but to explain you why this is a reasonable definition for the limit. And the idea is really in this tree encoding. So your cograph is encoded by a decorating tree. And in this encoding, the vertices corresponds to the leaf of the tree, and then you did the operation to add edges. Okay, you can think at it like that. And if I take these two leaves, when are the corresponding vertices connected in the corresponding cograph? It's easy, in fact, to answer this question. I just have to look when I do my recursive construction, when these two vertices are brought together, did I do a disjoint union, in which case they are not connected, or did I do a join, in which case they will be connected because I add all edges? So here, I did a join because I have a plus here. So here means what? In the first common ancestor between the two leaves, I had a plus, so the two corresponding vertices are connected. If I had a union sign, they were not. So you just have to look really at this youngest common ancestor in the discrete. That's how you can reconstruct the graph. And the nice thing is that you don't have to construct all the graph if you want to ask just if two vertices are connected. And so now, what is the continuous analog of that? So there is a whole theory of limit for random tree, which has been developed a lot in the last 30 years. And now, since in particular, this tree is in fact a condition branching tree or Galton-Watson tree, we know that it will converge to what is called Aldous continuum random tree. So what is that? I wanted to, let me redraw. I said it's coded by a Brownian excursion. So let me draw my excursion. So you take your excursion like that. And now I will identify pairs of points which are at the same height, and such that everything in between, they see each other. Everything in between is Eigen. And if you do that, you can imagine that you get a continuous tree at the end. And that's what is called the continuum random tree to infinity. And in this story, the leaves, which corresponded to vertices in the discrete, we can prove that almost every element 0, 1 corresponds to some point in the excursion, and it's in fact almost surely a leaf in the graph. So the leaf will be basically 0, 1. In practice, a measure 1 subset, but we can think it's 0, 1. And what is I want to look, when I take two leaves, I want to look at the youngest common ancestor. And if you think that you have, I take two leaves here and here, I have do my gluing operation, you can convince yourself that this youngest common ancestor will exactly correspond to the minimum of the excursion in this interval. And thus the definition is very natural. I just copy what I had here. I connect X and Y if the sign of the common ancestor is plus. Okay. There are some subtleties that I'm hiding here in the intuition is that, for example, here I had some alternation of the decoration. Here I told you I want to take IID decoration, but okay, it's still, I think we start to understand why this can be the limiting object. So if you don't like Brownian excursion, I have a good news for you. You can also describe, you have this Erdős-Hajnal theory. You can also describe, instead of describing your graphon, this Brownian cographon as a function, you can describe it as an infinite exchangeable graph. So I will more do the collection of finite versions for each n. So I recall you this GNWBR, it's a graph with vertex n, and such that I and j are connected if WBR UI uj is equal to 1. And my UI are IID uniform in 0, 1. So the thing which is a bit special here is that since I have value 0 or 1, I'm not saying they are connected with probability W, UI, UR, but just they are connected if it's equal to 1. Okay, there is no randomness in this stage, but what is also a bit different maybe that here we have a random graphon, so we have two sources of randomness. We have this W and this choose. Okay, but this gives me for each n a random graph, and in fact this random graph has a nice discrete description. Without any Brownian excursion, you can get it like that. What you do is you will take a uniform binary tree with n leaves, and I put random decoration, uniformly, independently balanced decoration. So probability half to get a union, probability half to get a join. And I don't have, you see, I don't have my previous alternating condition. So this means that from a tree like that, I can construct a cographs. But because I don't have this alternation condition, some cographs will be obtained from more than one tree. So I don't have, I have a construction, but I don't have bijection anymore. But okay, you can do that. You get a random cograph, which is not uniform because some cographs are obtained from more trees than others. But that's his distribution is exactly that of GNWBR. And this also means that if you want to prove that something converges to this WBR, this Brownian cographon, you can use the subgraph density criterion, and you can just prove that the subgraph density will converge to those of the to the probabilities, to the distribution, sorry, of this random graph HN. So you don't have to deal with Brownian excursion. In fact, the proof of the theorem, once you have this proposition, is just combinatorics. We do some counting argument, and we prove that we have the good limit for the subgraph density. But okay, the intuition is really that the excursion encodes the tree limit of the tree. Another nice thing, I will go maybe fast on this slide because I want to go to the independent set part. But another nice thing of this Brownian cographon is that, in fact, if you look at its expected degree distribution, it's just a uniform distribution in 0. And this tells you that if you take a random vertex in a random cograph, its degree will be normalized by n, will be asymptotically uniform in 0, 1, just because its degree distribution is a continuous functional on the space of graph. Okay, so now I go to the independent sets part. And first, I want to give a bit of motivation. So I said it's related to this Erdős-Hajnal conjecture. So let me tell you what it is if you haven't seen it.
Before you go on to the third part,
Yeah.
a quick clarification question. As you mentioned briefly, there are other graphs where r equal to 1. So do you expect, or maybe it is immediate, that in this case, all subsequential limits must be 0, 1 valued whenever r equal to 1?
Yeah, so that's a result in the paper of Hatami, Sekedi, and Jansson that I was citing. And it's also true if you avoid more than one graph as induced subgraph. And you can even avoid an infinite family. So it's true for every hereditary classes.
I see. Thank you.
With a good definition of R for such a class, which is not that trivial. Okay. So this Erdős-Hajnal conjecture says the following: if you fix your graph you want to avoid, then you have some epsilon such that every H-free graph contains a homogeneous size or homogeneous set of size n to the epsilon, and this means either a clique or an independent set. And of course, it's very different if you don't say that you want to avoid something. We know that log n will be best possible. So this is saying we have really, when you put some constraint, you have really bigger homogeneous sets. Okay.
Is that an asymptotic conjecture, or does it hold for n equals 1, for example?
If you take epsilon sufficiently small, you can make it non-asymptotic.
Okay.
Maybe then, if you want to optimize epsilon, it's better to ask the question: what is the better epsilon such that for n sufficiently large, we have something of size at least n to the epsilon. But if you like this, you don't need to quantify it.
Okay.
It's for all n. So when you have a conjecture like that and you cannot prove it, it's open. Sooner or later, you might ask, is it at least true for a uniform random graph? So, and it was proved that indeed it's true. If you take a uniform random H-free graph, it will have a homogeneous set of size n to the epsilon with high probability. And in fact, you have a bit more than that, that in most cases, so for most H, you have something which is of linear size. Okay. And the question is that, is it true for all H, of course? And natural, since P4 is special, it's also natural to say, okay, is it true for H equal P4? And that's basically the question we started to look at because we had already worked on this random cographs. And first, what we try is to do some kind of first moment method. Okay, so what you do is you fix some beta and you try to study the number of independent sets of size beta times n in a random cograph of size n. And because of this tree description, we can analyze that. And it turns out that you can compute the expectation. And this grows exponentially fast if beta is not too small. So you can even compute the exponential growth rate. So here is a small plot until it seems that until a bit more than 1/2, you have exponential growth. So this could indicate that there are typically large independent sets or independent set of linear size. But in fact, we realize also in parallel that it's not the case, that the expectation is misleading. So it's basically guided by a rare event, and that in fact, typically this xn beta n is equal to 0, or said other for any beta, or said otherwise, the size of the largest independent set in a random cograph is sublinear. Okay, and this, the proof of two. So I told you one, it's really a tree structure and analytic combinatorics, but for the proof of two, it uses the Graphon limits that I described a few slides ago. So I want just to give you a glimpse of how that works. Yes?
What is your previous stuff? You had this sort of approximating tree construction, right? Where you put IID uniform instead of like alternating uniform. Suppose you ask for that approximating tree, these questions, are they also?
I think the answer will be the same. So for two, I can tell you without any doubt, because what we prove is that if you take any sequence of graph which converge to this Brownian cographon, then it has a sublinear largest independent set. And of course, this approximating trees, this was a sample from the Brownian cographon, so it converged to the Brownian cographon. For one, we will need to redo really the computation, but I will be surprised if there is a qualitative change in the result.
You describe an independent set from the excursion?
I will, I mean, so it's, you have to take your excursion with the sign, okay? And then you have to take some set of points such that each time you take 2 points in your set, if you look at the minimum between them,
it's like
you have a minus. We don't have a more compact description than that, if that was the question. So, okay, there is a notion of independent set in a largest independent set, size of largest independent set in a graphon that was introduced by Ladi and Rocha. And it's really what you would expect, that an independent set will be a subset such that the graphon is equal to 0 almost everywhere on I times I. And you called alpha omega the maximum measure of an independent set, and that's an analog. Okay, if that's an analog of the size of the largest independent set divided by n. Okay, and a nice thing that they prove in this paper is that in fact this notion defines a lower semi-continuous function on the space of graphon. So meaning if you have a sequence of graphon which Wn which converge to W, then the limit or the limit sup of independence number of your Wn will be always at most alpha of W. So you don't have the reverse inequality. It's clear that you could take Wn is a constant 1/n graphon, and then it has 0 independent set, and it converges to something which is all 0, so as 1 as independent number. But in this sense, it works. If you have some large independent sets in Wn, you need to have a large independent set in W. And because of that, the only thing we need to prove that we have this sublinearity is that in fact our Brownian cographon has almost surely no independent set or no macroscopic independent set. That's its largest independent set is 0 almost surely. So just tell you quickly a bit how to do that. We need to use somehow, we really work in the continuous, and we use the property of the Brownian excursion to do that. And the Brownian excursion has a nice self-similarity property, which was discovered by Aldous. And here it's a very, I will be a bit imprecise, but it's a schematic view of it. So what you do is you take your Brownian excursion, simplify, and you take 2 random points U1 and U2. Okay. Then you look at the minimum between U1 and of the excursion between U1 and U2. Here for me it's B, okay? And I will look at the last time I was at the same level as this minimum, so it's A, and the next time I will be at the same level as this minimum, that's C. And when you have this, is break your excursion into 3 pieces. So the first 2 are easy to see, that's this one between A and B, this red one between B and C. And the third one, you have to forget and to merge the 2 extremal parts. And that's the nice thing that Aldous proved, is that these are 3 independent excursions, so you have to scale them. By this random length, it's just they just follow a Dirichlet distribution. And also you could say that, okay, the U is a random point in the blue excursion. You have a bit more. But for me, it's important that you get 3 independent excursions. So if I put sign on my excursion, this means that from one Brownian cographon, I can decompose it somehow into 3 independent copies of the Brownian cographon. And I will try to follow independent sets in this story. Okay? Imagine, so you have to imagine this card, some kind of graphon. And if I take an independent set of the large one on 0, 1, I can look at its restriction to the blue, red, and green part, and this gives me 3 independent sets of my smallest graphon. But here, if I have plus sign in the middle, it means that everything in the blue part is connected to everything in the red part. So if I want to take an independent set of the big thing, I have to choose. I have to choose either I take an independent set here or here, but I cannot take both. And because of that, I get this kind of inequality. So if when I had a plus, so this is the size of my largest independent set in my big graphon. This is the size of the largest independent set in the green part. So I have this rescaling factor, delta 0, which is the size of the green part. In the case where the sign of B was minus, I can take an independent set in both the blue and the red part. But if it was plus, I have to choose, so I have a maximum here. And I get an inequality like that. And I recall you, this WIBR, they are independent copies of WBR. So here, from this inequality, you get a kind of inequality for the distribution of alpha WBR. And we could prove that by using some kind of contraction argument and monotonicity, because we don't have an equation, but an inequation in distribution, an inequality in distribution. But we could prove that the only solution to this equation in distribution is the Dirac measure in 0, which means that this alpha BR is equal to 0, almost sure. So that's how the proof goes. I like that it goes through the continuous and the self-similarity argument. I find it pretty, but unfortunately, it does not give any control on the speed of convergence. And it would be nice to be able to say really what is the order of magnitude of this largest independent set. But it answers the question which was asked about this P4 free graph having independent set of linear size. So that's a pictorial summary of what I said, and I thank you for your attention.
Thank you very much. Are there any further questions?
So do you have any guesses for what that should be, the independent set, like square root n or something?
It's bigger. We've
Bigger
done
than
some
square root n.
simulation. Yeah, we tried to have some lower bound. And it's not that easy. We were a bit frustrating not to get something. So
the question is will it be polynomial in n?
So 2 weeks ago, I would have said it's n over log n. Now I have some doubts. It could be polynomial in n.
Okay. So then the graph unit will
So in the first row of your summary here, is there some graph for which the limit is known to be existing, like strangle free or something? So you said the limit is like
for H3 graphs, when you forbid only one H, I mean, I don't know if this has been written, but there are some very good description of like C4 free graphs and C5 free graphs in terms of split graphs and generalized split graphs, that almost all C4 free graphs are split graphs, if I remember well. And from that, you can get the limit here.
But if it's bipartite, then it's like 0, right? They have smaller and square edges. No? But yeah, I mean,
sorry, for then C4, it should be 0 here,
right,
I guess.
Right.
And for C5, I guess you will get a 0 and a 1.
I see.
If I should check what are exactly the structural result, but it's doable.
Maybe in terms of your nice Brownian limit, how can you see that P4 is not in it? It's a matter of interpretation, right?
I think it's not. It should not be. I mean, in the discrete, you can see that when you take your iteration or of union and join, you can see that P4 is not in it by just saying, okay, I have my 4 vertices. I look at the first time they are separated by some operation, and you have several cases to do. And I guess here it's a bit the same. So you take your 4 vertices in your excursion, you look at the first time they are separated by a minimum, and then depending whether it's minus and plus and how many vertices you have on each side, I think you can convince yourself that it indeed avoids
that either the path is not there or there has to be an edge.
Yeah,
somehow
exactly.
shortcutting it. Okay. Well, thank you very much.
I can ask. Oh,
Okay, during the coffee then. Thank you very much. Valentin.
You're welcome. Thank you.